Yesterday, yesterday feels like a long time ago. Yesterday we talked about the classical Ising model, and we said that the classical 2D Ising model, classical 2D, has a duality that map basically one value of temperature, say a low temperature regime to a high temperature regime, and vice versa. It also exchanges the lattice from a lattice to a dual lattice. In the case of the square lattice, the dual lattice is also a square lattice, and using this duality, we can compute, for example, the temperature of the phase transition in the classical Ising model. Now, when we learn quantum field theory, we know that a quantum field theory in, say, d+1 space-time dimension, when we formulate this theory in Euclidean space, the path integral is the same as the path integral of a classical stat-max system in d+1 dimension at finite temperature. One can ask whether the same thing happened here with the with the Ising model. Is there a quantum Ising model that is given that would give us the same that can be mapped to the classical Ising model in certain sense? And in this particular case, the answer is yes. If you go back to history, you remember that Onsager provided us with the exact solution to the Ising model, and one can formulate Onsager relation as a map from a classical Ising model to some quantum mechanical system. And Onsager did that through a technique called the transfer matrix. So the transfer matrix basically is, from the point of view of the quantum mechanical system, is finite time evolution in Euclidean space. So if you look at the any textbook, you will find how this solution is done. For the purpose of looking at the duality, we are going to I'm going to describe a quantum mechanical system that is not exactly the system that is obtained from the classical system through transfer matrix, but something that is very similar. Basically, one can think about that as a quantum mechanical system that belongs to the same class, universality class, as that of the classical Ising model. This one has continuous time. So the only thing that make it different is that time here is continuous, although space is still the system still lives on the lattice, one-dimensional lattice. Okay, so in the quantum model, on each we have a lattice, one-dimensional lattice. Each lattice site is I, and on each lattice there is a quantum spin 1/2 s. So here I have an Si, but Si now is a quantum spin. Maybe in order to distinguish that with the previous Si of the classical Ising model, I will call that sigma I instead. Sigma vector, where sigma is So this quantum spin in the I assume that is live in the S equal 1/2 representation of the SO3 group, spin group. So each of the spin can have can be in the spin up and spin down position, but since it's a quantum spin, that means that the Hilbert space, there is a Hilbert space of dimension 2 to the n. So each side of the lattice, we can have either up or down spin. It's a quantum system defined with the following Hamiltonian. So the Hamiltonian, I'm going to write down, is sum over sigma I plus 1, and here I sum over sigma x, and minus h sum over I sigma z I. Let me briefly tell you how this Hamiltonian arises from the transfer matrix. As when one try to solve the classical Ising model. So in the transfer matrix is basically a map. Basically, one write down the exponents E2 minus beta h of the classical system and decompose it into the product of different matrices. Each of the matrices can be thought of as a time evolution. We treat one of the coordinates in the classical Ising model as Euclidean time, and the other axis as space. And the partition function is interpreted as a trace of certain E2 minus h delta t. Well, let's say delta h to the power of n, where n is the number of time steps. And when you write down this delta h, you see there are two parts of this delta h. One coming from this link, horizontal link in the original classical Ising model. And that corresponds to this term, the horizontal link in the same time slice. And then there is these vertical links in the classical Ising model. And when you work out this map, we see that this one is this vertical links. These are the horizontal links.
What is H in the classical Ising model? What is H?
So it turned out, yeah, I can, yeah. I'm hesitant to say because actually you don't get the same Hamiltonian as this one, but it's actually a product of two different exponents. One is this exponent of E2 minus j sum over this x, and the other exponent is the time evolution across here. They are both related to k. When we make time continuous, we combine them into just one Hamiltonian. So the map is not exactly one-to-one. So, yeah.
Also, is there a reason why you wrote the vector for the spins? Like, I understand the matrices are vectors, but the spins can only be up or down, right?
The spin is only up and down. Yeah. So when
you
say
the same symbol sigma for the matrices and for the spins, is it?
Yeah, here it's a little bit. I mix up a bit of notation. So here, what live on the you can think about this on each side. This is an operator that acts in the Hilbert space at each side. And on each side, of course, the state that can live on each side is some kind of linear combination of up and down. The spin is an operator that acts on the sub-Hilbert space of a given spin.
Okay.
Yeah, how does the classical to quantum transition happen here? When we write down, remember when we do classical mechanics of a Ising model, we have to take a sum over all the possible configuration of spin, and that sum is interpreted as taking matrix product and taking the trace over a matrix of certain operator taken to the n power. So yeah, I actually don't know how Onsaker worked out his wrote down originally his solution, but this is how I would do that now. I first map it into a quantum mechanical problem of a discrete time evolution, and then solve for the eigenvalue of this Hamiltonian. Now, one thing, another thing that I gloss over is that when we do that, actually what we find is that in this term there is the term that we get here is actually product of sigma z. It's not sigma x, and this term is sigma x. But because of the rotational symmetry of the problem, we can rotate the basis to rewrite this into a more canonical form, where in the energy of interaction between two different spin we have sigma x, and the second term we have sigma z. And there is a reason why people like to write the Hamiltonian this way. Okay, so here this Hamiltonian has a discrete, so the quantum analog of the Z2 symmetry of the Ising model is a quantum Z2 symmetry. A quantum Z2 is the discrete transformation that map x sigma x at one place to minus sigma x and sigma z to just sigma z. Basically, one can think of a rotation around the z-axis that would flip the sign of sigma x. So the Hamiltonian is invariant under that Z2 symmetry. It's a discrete symmetry. It's not a continuous symmetry. There's no conserved charge in the usual sense that would commute with the Hamiltonian. Okay, so now in this model, what is important for the algebra? You can think about this sigma x and sigma y as object that satisfy certain commutation relation. So for example, one of the important things is that sigma x and sigma y, sigma z anti-commute at the same point. Also, for this particular representation, they square to 1. Sigma x square equals sigma z square equals 1. Now, one can now discuss duality. So now that it's possible to map this theory to another theory, basically rewrite the same theory in a different form. And that can be done exactly. So here, let me introduce new matrices. Let me call that mu x and mu y. So
just to clarify, you're considering this quantum mechanical system at 0 temperature. In the quantum
in
mechanical
this
system.
case, we can just think about this as a quantum mechanical system, and whether one pose a question of 0 temperature is and of finite temperature, it's our choice. If you have finite temperature, the equivalent Ising problem would be Ising model on a cylinder. That would be a equivalence of this Hamiltonian in finite temperature.
I see. Okay.
Yeah.
Thanks.
So, but this duality that I'm going to write down is going to be valid for any temperature, doesn't know about temperature. So I'm going to define new spins that lives on the dual lattice, which in this case is just the side in between the side of the original lattice. And I will define the spin this way. So mu z at side n plus a half is the product of 2 sigma x at side n and sigma x at side n plus 1. And the mu x at side n plus a half is the product of all sigma z side n side I with I less than n. Here I assume that the system has an n, so this product is from 0 to n. So it is now an easy exercise to check that these mu satisfy what is needed for the for it to be the z and the x components of spins on a local at each side. Namely, you can check that mu x, for example, mu x and mu z at the same side anti-commute. And they anti-commute only when these two sides are the same. And the operator would commute otherwise. And they square to 1, for example. All this can be checked. It's an exact mapping, but one thing that we see here that the map is non-local. That is mu x, for example, is expressed in terms of the product of all the z component of in the other representation from basically from one end of the sample to that point. And then one can write down the Hamiltonian. So now you see the minus h times sigma z term in the other representation. So now can be written as sum over I now mu x I plus 1 minus j sum over I mu z of I. So that the second term mapped to the first term in the previous Lagrangian is pretty obvious, but that this first term in terms of mu xi and mu xi plus 1 also mapped to the second term in the previous Lagrangian is almost trivial. So here you see the map that we have. Basically exchanges the role of h and j. H becomes j and j becomes h, and that has a consequence for our interpretation of different phases of the theory. So let's consider the situation in which j is much larger than h. So we know that this j multiply the product of 2 sigma x, right? And that term dominate in this regimes. That means that the spin want to be in such a situation in which the x components of spins point to the same direction. The ground state would like to be in the state where the spin all spin have the same sigma x. So this is a situation of Z2 symmetry breaking. The ground state breaks Z2 symmetry. Sigma x is equal non-zero. And the ground state doesn't map to itself under the Z2, which map sigma x to minus sigma x. This is in one description, in our original description, but what happens if you go to the mu description? In the mu description, obviously J is now the new J, because J and H are exchanged in the new description. J is much smaller than H. And here, the new phase is a phase in which we should associate this phase with the phase where Z2 symmetry is unbroken. So it is the strange thing here that the duality map Z2 broken phase in one description to a Z2 unbroken phase in the other description.
I would have thought that you fix J being very, very bigger than H. And then when you do the transformation, as you write the Hamiltonian, the second term in the mu description.
This J, let me call that J mu was equal to the previous H, and H mu is now, in the new description, this let me call that J mu, this is H mu. But the thing is that these two phases map to each other. In the same system, we have two, the same system can be described in two different languages. In one language, we have an expectation value of a certain operator. In the other phase, this operator has a zero expectation value, but another operator, which is non-local with respect to when we write it in terms of the previous operator, now have an expectation value.
So is it clear that the Z2 is the same Z2? Because in the other description, the Z2 acts on mu. The Z2 that is unbroken acts on mu. Whereas in the first description, Z2 acts on sigma.
Yeah.
So they look like they are different Z2s.
Yeah, it's a different Z2. Yeah, the Z2 that is broken, another Z2 when it maps that map mu into mu x to minus mu x is the one that is broken. Nice thing about the Ising model in 1+1 dimension, this quantum Ising model, is that it makes a lot of strange things about quantum field theory very explicit. This one can work out step by step the map between two sides of duality, and then look at the operators. Actually, this model can even be exactly solved, can be solved exactly. So when probably I will not tell you in detail how to solve this model exactly. The exact solution is by fermionization. That is by mapping the spin operator to fermions. Maybe I write some note and then outline how that can be done. But you can also look at Jordan. I think it's called Jordan Wigner. If I'm not mistaken, this transformation. then map spin into fermion. And in terms of fermion, the theory is just theory of non-interacting fermions, which can be solved exactly. And again, in this fermionic language, one can see the fact that the two model has the same spectrum. This two model with J and H exchange have the same spectrum. Okay, is there any other questions? Not, I'm going to go to one more dimension. Now we are going to think about system in living in three dimensions. So it's either classical, so it's classical system, 3D classical system, which are equivalent to 2+1 dimensional quantum field theory. So maybe I'm going to write down a result first, and then try to show you how much we can do to justify or derive the result. So the result that I will argue should be true is the duality between two theories. Now, these are not lattice theory, but these are full quantum field theories. So on one side of the duality, we have a field theory given by familiar Lagrangian. I'm going to write it's everything in Euclidean space. 1 plus m squared pi plus lambda pi to the fourth. And on the other side, I have another theory where the Lagrangian is given by almost the same 1 plus tilde pi square plus like lambda tilde psi to the fourth plus 1 over 4 e square f mu u square. So one theory is the complex scalar field. Another theory is, so we would call that the abelian Higgs model. Usually these are very different theories. They are dual in the following sense. In the complex scalar field theory, there are two different phases which can be thought of as a phase where the potential doesn't have has a minimum at 0. So it's, and the other phase where the potential looks like a Mexican hat potential. So since the scalar field is complex, there is a manifold of vacua, degenerate vacua parameterized by a phase. So I call that the so this would be a spontaneously broken phase, and this is a spontaneously unbroken phase. So in between these two phases is a phase transition. At the classical level, that phase transition happens when m squared is equal to 0. Right? So here it would be m squared larger than 0, and this is m squared smaller than 0. The reason I wrote this equality or inequality in quote, because we know from quantum field theory this m squared receive the radiative correction. So this would have, we have to compute this diagram to get the effective mass of the particles. And when we write m squared equal to 0, it implies some kind of a renormalized mass, not the original mass in the Lagrangian. So the statement of the duality is that in the vicinity, if we think about changing the mass from one side to the other side, the vicinity of this point, the vicinity of the phase transition as a function near m squared equal to 0 is the same, is governed by the same physics as the vicinity of the transition between two different phases in the abelian Higgs model. But in the abelian Higgs model, there are two phases again, which can be thought of as a phase where we have no symmetry breaking. But when we say symmetry breaking, we have to be very careful. Here is the gauge. The symmetry is gauge. So whenever we say there is a Higgs wave, etc., that these statements are not gauge invariant. So here I'm using a intuitive but somewhat non-rigorous description of the phases. So in one phase, this m tilde square is larger than 0. Again, this m tilde square smaller than 0. All right, and here again, if we think about this m tilde square is something that runs, the vicinity between these two phases of the transition between these two phases is claimed to be governed by the same physics as the vicinity of the transition in the first theory. Now, one thing that is not trivial to check is the mapping between the spectrum of the on the two sides. We know that in the complex scalar field theory, on this side, on the spontaneously broken phase side, there is a Goldstone boson. A Goldstone that is massless, which disappear at the phase transition. Here, on the other side, we have massless photon. So this massless photon in 2+1 dimension has only one polarization, in contrast to the photon in our 3-dimensional space. The polarization of the photon is a spatial direction perpendicular to its momentum. And so we can see here that there is at least at the level of counting the number of massless degree of freedom, this phase, which we call the Coulomb phase, mapped to the Goldstone phase of the complex scalar field theory.
So when you say it's dual, are you tuning the lambda and lambda tilde and E? Because there are two couplings on the right hand side and one coupling on the, you're tuning.
There is one coupling on this side, it's lambda. So so here maybe we'll discuss a little bit what we mean by the what is the phase transition. So in the complex scalar field theory, okay, so here I'm drawing the space of the some kind of space of two parameter a plane that each of the point correspond to a certain value of mass and lambda. So say here I'm going to put the lambda, here put, for example, lambda, right? The renormalization group flow would take us from some along some trajectory in this two-dimensional plane. So let's ignore all the other interaction, keep only mass and lambda phi 4. So the phase transition corresponds to a point, roughly speaking, when m squared is equal to 0. So I'm going to put this point here. But that point also is a fixed point in lambda. We call that lambda in 2 plus 1 dimension. The naive dimension of phi 4 coupling is relevant. This coupling is relevant. So lambda grows as we start from some small lambda, will grow. So in the UV, you can imagine the following. In the UV, we start from some point here. So here is our UV theory. We start with the theory, you would say, negative mass square in the bare mass. And then we run, when we run the theory in the infrared, the mass square got the radiative correction and becomes larger and larger, less negative and negative. Okay, so the critical theory is obtained when we fine tune this mass so that it goes directly to this point. Go to this point.
This is not a stable point in the RG sense, right?
It has one relevant deformation. This fixed point has one relevant deformation. We have to fine tune one parameter to tune to that fixed point. Okay, so if we start from somewhere a little bit larger, then we will find that this renormalization group flow will take us to some m square that is here. That is positive. If we start from somewhere right here, it will, the renormalization group flow will take us to here. So this corresponds to two phases. This is spontaneous symmetry broken phase, because m square is negative in the infrared. This one is spontaneous symmetry restored phase. There's no spontaneous symmetry breaking. This is our understanding of the phase transition in the complex scalar field theory. Basically, it is one member of quite a simple class of ON model. This model is O2 model. O2 because the U1 symmetry of complex scalar is O2, which can be generalized to ON. When n is equal to 1, basically it's an Ising. It's an Ising model. When n goes to infinity, the problem can be solved exactly in another way using the 1 over n expansion. Analytically, we can do either ON when n goes to infinity or epsilon expansion in 4 minus e equal 4 minus epsilon. But we know that the qualitative behavior that we get from epsilon expansion holds in 3 dimensions. The phase diagram, the features of the fixed point, the structure of the renormalization group flow is the same. Okay, so okay, yeah. So the claim here is that if we start so the claim here is that the abelian in the abelian Higgs model, if we start from the UV appropriately, we can reach the fixed point. So I'm just drawing some very schematic, because here I have m tilde square, have lambda tilde. I also have E square. So the claim is that somewhere in this diagram there is a point. Somewhere here, let me just again put it, maybe I put it somewhere different schematically, because the somewhere here, for example, there is a fixed point, and there exists this fixed point, and that we can approach it starting from some UV, from the UV theory near. So the UV correspond to small lambda, small epsilon, small e, e square, the coupling constant. So we start from some value of the mass, and then we can reach this fixed point just schematically this way. And all the critical exponents between the two sides should coincide. So the critical exponents, one of the critical exponents is how the correlation length diverges as a function of the tuning parameter. So the correlation length should grow as one make the bare m square to be equal to the critical value of m square, and that I think the parameter here is called nu. And the claim is that here I have the same nu, same critical exponent, and all the other critical exponents, not just nu. Now you see this has a very different flavor than the duality that we have talked about in the Ising model. Namely, these two theories, the theory in the UV, are completely different. In the UV, one theory has a theory of a scalar field. In the UV, the scalar interact weakly with each other. Because the interaction is relevant, 5-4 interaction is relevant. In these two theory, one theory contains an additional photon, but as we flow these theories to the infrared, it's possible that they would approach the same fixed point. Okay, so maybe I'll stop here with this field theory description, and then we'll continue a little bit later. But I want to give you the flavor of how this duality, what we should expect for this duality. So this duality has been found or argued to be correct in a couple of papers, one by Peskin, I think in 1978, and the other by Harper in Dasgupta, 1980. As far as I can see, they didn't know about each other's work. then, but they are essentially the same. They are exactly, they were talking about exactly the same duality. Okay, so what I'm going to tell you here follows more or less what is written in the paper by Peskin, Annals of Physics. Maybe in slightly, but it's almost the same as what's written in Peskin. So the starting point of the goal of this work is to argue using lattice model that one can map one lattice model one, which can be thought of as some discretization of the complex scalar field theory, of the phi theory, is exactly equal to another lattice model 2, which is a discrete version of the abelian 6 model. Now let's say, let us say right away from the start, even if one can prove that, that doesn't necessarily prove the field theoretic duality that we have formulated, because we have to additionally prove that this lattice model has a fixed point, and that fixed point mapped to the same fixed point as the fixed point here. So we'll see that it's an additional, this is an additional complication that, or an additional assumption that we have to make. Okay, so let's see how far we can go with this program. So when we start from a lattice model on this side, we can start by discretizing the scalar field theory. But it turned out to be not the most convenient. There are too much complication. The lattice model, we want this lattice model to be as simple as possible. In order to do that, we use statement of universality, which used to be called the hypothesis of universality. But now most people believe this is true, that a critical point in a field theory depends only on the symmetries of the order parameter, but doesn't depend on the detail of the theory. So the critical point, fixed point, all the properties of the fixed point depends on symmetries only. In our case, it's a phase transition where this O2 symmetry changes from being spontaneously broken to spontaneously unbroken. And that suggests a simpler, or at least the simplest, I think the simplest model with this is a lattice generalization of the Ising model, in which at each point on the lattice there is a O2 spin, not a Z2 spin that can point only in up and down direction, but a spin that can point in any direction on a plane, parameterized by an angle theta, basically, theta I. So the Hamiltonian of this model is minus some, let's say, let me just put the overall coefficient in front to be just 1. And here I have cosine of theta I minus theta j, sum over all the neighboring pairs of neighboring indices I and j. Z would be equal to, again, sum over the whole partition, the whole ensemble, which is now integral over all d theta I, all d theta I, and then I have E2 minus beta sum over ij cosine theta I minus theta j. This model is also called the XY model, because here we can think about each spin as a unit vector in an XY plane. So that's why it's called the XY model. Classical
that is three-dimensional, right?
The lattice is three-dimensional, yeah. So the lattice is three-dimensional, but it's hard to draw. Try to do that. The three-dimensional lattice. The spin is point in a two-dimensional, as two components. Yeah, so this is the seems to be the simplest model, that when beta or the temperature is high, beta much less than 1, for example, we have a phase, disorder phase. And when beta is much less larger than 1, that is when it costs energy to have the spin pointing in different direction. We have an order phase. In 3 dimensions. There is no theorem that forbids such a transition in 3 dimensions. So this XY model can, in principle, we can do many things with this, but so now that it's really much more convenient to modify this model a little bit, make it more suitable for duality, while preserving all the symmetry of the model. That is to go from this XY model, simple XY model, to the so-called VLAN model. Which makes a lot of formulas that I'm going to write much simpler. So in the XY model, there is this E2 minus beta cosine of theta. Basically, right? We have this theta equal theta I and j. And the partition function inside the integral is a product of this function E2 minus beta cosine of theta, and theta is the difference between the angle in the two sides I and j. So this function, if I plot this cosine theta, would have some form, it's a periodic function with maximum around 0, 2 pi. But cosine is, I should have plus, sorry, because the Hamiltonian has a minus sign. So E2 minus beta is plus. E2 plus beta cosine theta is a periodic function like this. And in the VLAN model, this periodic function is replaced by sum over n, and then E2 minus beta over 2 theta minus 2 pi n square. So the VLAN model replaces this function by another function, which is also periodic. And it has the same kind of behavior near each of these maximum. I choose the coefficient here to be beta over 2 so that it mimics the exponents of the E2 minus beta cosine each point. So it's turned out that it's easier to start with not the original XY model, with the VLAN model, and all the transformation is simpler. So Z in the VLAN model, let's write down what is the partition function. So the partition function is again integral over all spins.
Sorry, can we explain how this is periodic?
Oh, this is periodic because we have sum here of over integer n, right? So if I take, so if I call this function say z of theta, and I change theta
I see.
by 2 pi, clearly this can be compensated by changing n. Yeah, so it's a periodic function. So basically, it's a sum of Gaussian. Right?
Yes.
You see, all these are Gaussian shape, but I superimpose a lot of these Gaussian on top of each other and mimics this exponent of the cosine that way. Since universality tells us that nothing depends on details, the fact here is that we still have a model, which I'm going to write down, that preserve the O2 symmetry is important, is the only important thing. Okay, here I have, instead of products of these exponents, of products over all the pair xij of this function. This function, each of these function is a sum over n, let's call nij, and then e2 minus beta over 2 theta I minus theta j minus 2 pi nij. A little bit cumbersome, but that is our partition function. Now I'm going to outline how we can perform a duality transformation on this model. So first of all, this integral over theta, originally they go from 0 to 2 pi, right? But without losing any, but I'm going to extend the range to minus infinity to plus infinity. The reason I can do that is that basically if I have this extended range from minus infinity to plus infinity, I can the partition function, what stay inside the partition function has a gauge symmetry, some kind of discrete gauge symmetry, in which I can change theta I to an integer, theta j to 2 pi times an integer, 2 pi times another time integer, and nij can be changed to nij plus ni minus nj. And by using this gauge, I can map any configuration of theta to that where theta is between 0 and 2 pi. So basically here I introduce some trivial infinite factor, which can be factored out by choosing a certain gauge in which theta is between 2 and 0 and 2 pi. Okay, so I can think about this integral over theta as from minus infinity to plus infinity without any problem. Now the square here. Yes. The first step that most crucial step that Peskin did is to rewrite this Gaussian through an auxiliary integral over an auxiliary field. So I have original integral over theta variables, but I'm now introduced new integral over some variable bij. That lives on the limit, and rewrite this exponent as a Gaussian exponent over b. You can check that this is what the following will give you the correct answer. So here what is being integrated again is so this we have to keep from minus infinity to plus infinity, each of that, and then here each exponent going to write down minus beta ij square over 8 pi square times beta plus I bij over 2 pi times theta I minus theta j minus 2 pi nij. Okay. Well, you can mentally try to integrate over each of these d beta, db here. And the integral here is completely Gaussian. And this Gaussian integral gives rise to this exponent of this expression square. Now, at this moment, we just do a complete introduce just unphysical auxiliary field, which no dynamics basically into this lattice theory. And the value of these introduction is now we can do integral over theta. The integral over theta is particularly interesting. So this we see each of these theta I in this expression multiply the b that is adjacent to it. So this b ij. So now that if we introduce this b, there are 6 of this b that adjacent to each of these theta that would contribute. And when doing this integral over d theta I, you find that sum over n, I'm sorry, b ij, where j is neighbor of I, has to be equal to 0. The integral over the theta is integral of, it's like what would give the delta function. Set a delta function. It's delta function of sum over bij over j that is a neighbor of I. Here, bij is equal to minus bji.
You seem to have frozen. Is that just me, or is everyone else experiencing that?
Same for me. Yeah.
Yeah.
So
We lost him.
Looks like
Yeah,
he
okay.
disappeared. I feel like when there's a bad lag like that, it's almost better when he gets kicked out, because then he knows that he's
can you hear me now?
Yeah, we can hear you now. We
So
lost you for
okay.
a little bit.
maybe the last minute.
You lost
A minute. So I was explaining that integrating over theta, the original theta fields give rise to a constraints on B. Basically, the sum over B that comes out from one side is 0. It is some lattice version of the statement that B is a vector with a 0 divergence. So that's that is the statement. That is the delta function that we get. So we can do integral over theta. So introducing this, there's the reason why we introduce the new variable is that we want to integrate over all our variables. So we can do integrate. We integrate over this and get here instead of so this term would disappear. instead we have a constraint that roughly divergence of B is equal to 0. Delta function of the divergence of B. That's what we will get. But now this condition can be solved on the lattice. And that's how the gauge field of the dual theory, the our U1 gauge field of the abelian Higgs model is going to appear. Basically, B is going to be curve of A. But on the lattice, it looks like this. On the lattice, let me draw a lattice. So B lives on a length. And I'm going to introduce dual lattice with sides that have, instead of having integer coordinates, now have half integer coordinates. On the dual lattice, this B, this line go through square. And I'm going to introduce my field A to live on the each of these links. Then this statement basically says that B of this length is going to be the flux of A, that is B colon ij, is equal to B, let me call that ABCD axis, AB plus ABC plus ACD plus ADA. That is basically the integral of the integral of A over this over the border of this line. So you can check if with this definition and the asymmetry of A under exchanging the indices, the sum over all lines that go through, that go all the B's that go from one particular vertex, it's going to be sum of the circulation of A around the side of a cube and sum up to 0. So that's how the constraint curve of B is equal to 0 can be solved on the lattice by introducing a gauge field A now living on the links in the dual lattice. Okay, so that's I think that is the most crucial steps. I'm not going to go further. One can follow Peskin, but I want to point out. I want to tell you what will happen. What can happen in the intermediate steps? How far one can go. So how far one can go is that we can represent this Z as a sum over all configurations M. So that let's call that M. Call that called Mij. Some after certain introduction of certain other auxiliary field, playing with that, and then the it's sum over all configuration of M. This M is a discrete field, so they are like from minus infinity to plus infinity, but have discrete integer values. And then, roughly speaking, we have this integral over DIA, path integral, but discretized. And then the action is exponents of minus, something very similar to the Maxwell action. Discretized in placket, sum over placket, plus sum over ij, which is Mij, Aij with an I here. It's some 2 pi that I'm. And in this sum, there is a constraint of, again, diff of M is equal to 0. this is actually how far one can get at the when we insist on exactness of the transformation. All that's happened later required certain physical intuitions or approximation, combination of both. So here, yeah.
Tim, you have about 5 minutes.
Sorry. Yeah, I have 5 minutes.
Yeah.
Okay,
Mhm.
so I'm going to finish here with this. I'm going to interpret this M. So this M is something that has divergence equal to 1. I'm going to interpret this M. Let's imagine that M can be either 1 or minus 1. When divergence is 1, then it's basically some kind of line on the lattice. And this is 1, this is 1, and so the divergence here is 0, and here is. Let's consider just, although M can be 2, 3, etc., consider the case when there is a continuous line of M equal to 1. And that line can be interpreted as a word line. I'm going to interpret it as a word line of a charged particle can be interpreted as a word line of a charged particle interacting with A through term here, which is now nothing but the discretized version of dx mu A mu of x exponents of the Wilson line associated with this particle. And so we can imagine that if we know how to solve this theory exactly, that will map to some kind of a word line formulation of a theory of particles interacting with a gauge field. This word line can be thought of as creation of particle hole pairs, or particle goes from minus infinity to plus infinity. So that's the step that required a certain physical intuition and argument. But at the end, if we can see the goal, at least from here, we can see the endpoint, that is the abelian 6 model, and that's what Peskin and Halperin Dasgupta argue at the end, that this lattice calculation suggests that there is a duality between two scalar field theory, two bosonic field theory, one complex scalar field and the other is abelian 6 model. So right now this duality sometimes called the bosonic particle vortex duality. I will explain why it's called particle vortex duality next time. And then next time I will jump to more modern topics of fractional quantum Hall effect and fermionic particle vortex duality. Any question?
Thanks a lot for that. Let's have some quick questions.
I have one. How do I see that this is a U1 gauge field?
So this A here is through its introduction. Here, this A is basically a discretized version of the Wilson line. So it's like discretized version of A mu. Right? B is so it's a curve. I'm not sure I understand your question. It's clearly not a non-abelian gauge field.
Because there is no, like in the field strength, there is no like other terms. Is that? Is that why, right? But
It's just one component of the field strength, which is B, and the its energy, its
I think we lost you again.
yes, I think.
action is. You lost me.
Yeah, we hear you now, I think.
Hello.
Yeah.
Yeah.
Go ahead.
Yeah. So so from this map, we can see that this gauge field is just U1. It's not what appears here is just abelian gauge field, non-compact even.
We again lost you. Maybe it's because my video was on.
Well, I think maybe we'll stop the recorded questions with this one.
Although all the
hopefully come
charges
back.
that